All right, so let's look at the solution to the homework assignment or the quiz real quick. Write a method named isThere that takes an array of ints as a parameter and an int to search for. Start with just that. Actually, well, we'll come back to that here in a second. Well, the method should return true if something is the case, false otherwise. So the return type is Boolean. Name of the method is isThere. It takes two parameters, an array of integers and an int. So given that information, we should be able to come in here. Static, Boolean is the return type. isThere is the name of the method. Int array is the one parameter. And int val, an integer you're searching for, is the other parameter. So every single one of you should have been able to start off with that. Or something along those lines. You could name your variables differently if you'd like. Okay? You're supposed to return true if val is found at least once in AR and false otherwise. Something along those lines. So for loop that goes through potentially every single bucket in AR. Each time through, if the current bucket we're looking at is equivalent to val, that means we found it at least once. Go ahead and return true. End the method immediately. If we get through this entire minefield and never find a match, we'll be still alive here and we'll return false, which means it was not found. Make sense?
Yeah, but won't that return true for every instance where they find it?
No, because return makes a method immediately end.
Okay.
First time you find it, the method's over. Very first time. All right, questions on that? All right, do we have a homework assignment?
No.
Are you lying?
No. You remember I bribed you with coffee?
That's right. I'm a little angry with my 390 class for lying to me. My I had a homework assignment in 390, and I did the same thing as I did in here, where if you did a good job in the homework, I wouldn't give you homework over Thanksgiving. Only about half the class submitted the homework assignment in 390. Yet they swore up and down in class, "Oh yeah, we did it." Blah blah blah. Did you submit?
Yeah.
Are you lying?
Well, I wasn't. Wait for.
It's the cryptocurrency class.
Oh no, I didn't. No, didn't get that paper.
Did you
I
submit?
wasn't in that class though.
So,
The one that was due on Wednesday.
wait.
The paper.
The paper that was due on Wednesday.
Oh. Because didn't you do another one or something after that?
No, Wednesday was the last time you had that class until yesterday.
Oh no, I was sick on Tuesday and Wednesday.
What doesn't mean you don't submit the paper?
Couldn't do.
Just means we didn't swear up and down.
How many? Who else in here is in 390? Did you do the paper?
The paper on the Genesis block?
Yeah, the one that's due Wednesday.
No, I've got most of that.
Who else? Who else? Did you do it? It was due last Wednesday. Now the funny thing is out of this small sampling, I said that about half the class did it. 0% of the people in this class. Now you remember me saying that if you did good on the paper that you wouldn't have an assignment over break, right? Remember? Should I punish this class now?
No.
Ay, ay, ay. All right, so we didn't have homework?
No.
If I remember correctly, I am all caught up on grading, by the way. Every one of your assignments is graded. If I remember correctly, I think most of you did the homework that was due right before break. So this class earned it. The 390 class will be punished tomorrow. Severely.
So we shouldn't. So nobody should be in the wing of computer science.
We're gonna have basically an hour's worth of back to back quizzes. Progressively more difficult.
And then on top of that, a homework assignment.
Oh yes, definitely a homework assignment. What's up? Oh, did you ask them why they said something?
I said, why would you say something like that?
Why?
To the other class's problems.
Why not? Well, it's like a warning of what could happen, right?
It's like putting someone's head on a stake.
This could be you. All right. So since we didn't have homework, I want to start talking about objects. Last thing we were doing is fraction stuff, right? Okay.
Tell us about Euclid's algorithm.
Euclidean algorithm. Yep.
We need to finish the other one first.
The who?
The square root thing. We never finished that.
Didn't finish that.
Yeah.
Oh, that was supposed to be the quiz, wasn't it?
Yeah, no, I was.
Everybody take out a sheet.
Say somebody was supposed to come up with how square root can be used to make the problem of finding greatest common divisor simpler
Without using the algorithm.
without using Euclidean's algorithm. Go ahead.
Can you rationalize the square root and use that to find a simple answer?
Okay, tell me more about that.
So you basically break down the object of the square root, say 12, and you break it down into 3 times 2 times 2, and then you break that down into 2 to the 2 to the 2nd times 3, so then you take square root of 2 to the 2nd times 3, and then you can use that to find top over bottom, and then you find the common denominator.
Okay, so how are we actually going to use the square root in that case, though?
Yeah, I'm not sure. That was the problem.
Anybody else?
Couldn't you just multiply the denominator by itself to get rid of the square root and then find the lowest common denominator like that?
Multiply the denominator by itself.
Yeah, because it gets rid of the square root then. And then there's the square root in the numerator, but you just want to find the lowest common divisor.
So you want to just put a square root around the numerator and the denominator and then multiply the denominator by itself?
No.
Like, I mean, I get what you're talking about algebra stuff. But I get, what does that have to do with it? Nothing? All right, quiz next class will definitely be on that. Somebody remind me, otherwise just everybody gets zeros and head on the stake. But from a different class, a different head. What?
What if I bring you coffee?
Well, you can bring me coffee too, and maybe then you won't have 2 quizzes. I was just telling some people in the cafeteria this morning that this is the time of year when faculty really should be increasing the amount of stress on students, I think. Right? Isn't this like the least stressful time of the year for you?
No. You know how hard it is to organize studying with deer season?
Well, have you?
Shotgun and antlerless opened up yesterday.
Yeah.
Yeah, I got
Antlerless.
Yeah. You can only kill babies, mom.
Okay, so yesterday was babies and mom season.
No, just moms.
Just moms. Oh, you can't kill babies still.
You can never. I mean, the meat's really tender, but it's frowned upon.
Is it frowned upon or is it illegal?
If they're a year old, you're good. If they're younger than that, it's frowned upon and illegal.
Okay. So right now you can kill female deer,
Yeah.
but male season's over.
For a couple weeks.
Well, then we start calling that herd again.
soon as the next rut starts.
The real question is when do I start getting venison bacon and venison jerky and venison steaks and?
As soon as I say screw the gun and get hit one with my car. Because apparently I can't shoot one.
Oh, oh. See, I have a bunch of other students who are hunters, and they've already like got their limit or something. So you
I
just
only go out for the late season.
I see. So you're like going for scraps.
I don't like dealing with other hunters because I only have private public land to go on.
Okay.
So I go for the late season because like nobody around here goes out for antlerless.
So there's already less deer, and then on top of that, the deer that are left are the smart ones that were able to avoid the hunters already.
Yep, and there's no other hunters hunting them. So
Well, it's because they've already got their deer.
that's why
They killed the dumb deer.
That's why I take, like, jug of molasses or sugar out there and just bait the deer.
Isn't that illegal?
Nope. Not in Wisconsin.
Oh, it used to be?
Yeah.
Yeah.
Indiana, it's still
Well,
illegal,
yeah,
but
in a couple of states.
Yeah.
They just made it legal in Michigan like 2 years ago.
in Wisconsin it's legal. I was like, oh wait, I can use these.
All right. So in any case, next class, you will have a quiz. And the quiz will involve telling me how we can use the square root to reduce fractions in a more time-efficient way.
Can we have any hints?
Huh?
Can we have any hints? I mean, I tried researching it.
Can you have any hints? I've given you a bunch of hints. I mean, the main hint is the goal is to reduce the number of things that you're going to be testing. So if you have two numbers, a numerator and denominator, right now we're finding out the smaller of those two numbers, and we're testing every single number between 1 and that number. Every single one of them. So how can the square root be used to reduce the number of numbers we have to check? That's the question. I guess that's the hint. That's a bad hint. I don't know how I can give a better hint without like giving away the answer.
I'm not sure if you told us the answer, we would know what you're talking about.
You would. It's like it's crazy clear. I think you're making it more difficult than it has to be.
So like your glass is clear?
Yes.
A little foggy.
Little bit of hints.
All right, so here in our reduced fraction, well, technically we're, this while loop right here is just going to keep reducing smaller over and over again, but reducing it by 1 over and over again until we run into a situation when both the numerator and denominator are evenly divisible by smaller. And we know we have a stopping point there because smaller will eventually become 1. Correct? It'll eventually become 1, and then we know that the numerator and the denominator will both be divisible by 1. So we know that this is not an infinite loop because of that fact of math. Okay? What I'm saying is instead of going down by 1, we need to reduce the number of numbers that we're going to look at. Right now, we literally look at every single number. Every single number. So, I mean, can I give you an example without just giving you the answer? is the question. I don't think I can. It's like so trivial.
You just square root the whole fraction.
Rather than subtracting 1 from smaller, could we just square root it every time and then use the result from that? Because that'll cut out a lot of options.
You're along the right path. I mean, you kind of overly simplified that and just kind of spitting words out, but that's That's not horrifically far from the answer. The square root plays a major role in reducing the number of things you have to test. All right, so that'll be the quiz next class. Quickly, just so we don't burn too much time talking about it.
You don't have internet.
Huh?
You don't have internet.
Oh, that's true. You got this.
Did you ever figure out what I was sending you last night?
No, I never looked at it. But I mean, I looked at what you sent me, but I never looked at it when I got onto campus or anything. All right, so Euclidean algorithm. Actually, is this going to give some of it away? I won't say anything, but there might be aspects of this that give a little bit of it away. So that means pay attention. Just aspects. This won't directly do it, because this is substantially better than the square root method I'm talking about. Somewhere in here, they're going to have the actual algorithm. Here we go. So, couple of functions. So here's the implementation of it in pseudocode, but we can write this. So if you want to get the greatest common divisor, now we're reducing fractions, right? So the greatest common divisor is going to be the one number that evenly will be the largest one number that evenly divides both the numerator and the denominator. Okay, so in this example, we would pass in the numerator and the denominator as our two parameters to greatest common divisor. And whatever number that spits out, which will be some integer, that'll be at least 1, right? Some integer, we can then divide both our numerator and denominator by to get us a reduced fraction. Okay, so that's what this function is. The Euclidean algorithm is a function for not reducing fractions necessarily, but for determining the greatest common divisor of two numbers. All right, so we take in two numbers, and as long as b, the second number, so if we think about this is our denominator. As long as the denominator is not equal to 0, that's if we pass in numerator and denominator. You could always pass in denominator and numerator as well. Doesn't matter. Any two numbers we pass in, it'll find us the greatest common divisor of those two. Okay? So, as long as, in our example, the denominator is not equal to 0, we're going to set another variable, t, equal to whatever our denominator currently is. Then, make our denominator smaller by taking whatever the numerator is and modding it by the denominator. Okay? Then we're going to set our numerator equal to whatever our denominator used to be. Go ahead. You mean to write this version?
No, the other version using the square root.
I will next time. Yeah, because that's your quiz.
Okay.
Yeah. Yeah, next time I'll write the square root version after you've answered it on your quiz.
Oh, so we'll have to code it on the quiz?
No, the quiz you can just tell me.
Okay.
Although coding would be just as easy. I mean, it really is trivial. It's kind of. I mean, it's not quite the 390 head on a stake thing, but it's close. So don't overthink it. All you're trying to do is reduce the number of things you're checking. The square root solution is not the best solution. This is. Okay, greatest common divisor Euclidean algorithm is the better solution for determining the greatest common divisor of two numbers. But the square root version is a far better solution than brute forcing every single number between 1 and the smaller of the numerator and denominator. Okay? So that's kind of the middleman solution. And that square root solution typically works for most problems. For instance, last class, I think we ran a couple of scenarios where it was taking a long time, right? Had we used the square root solution for that, in most of those circumstances, it would have seemed to happen instantly.
So the square root solution, would you just look at the smaller number?
Maybe. The short answer is yes. The long answer is you wouldn't necessarily have to, because doing the square root based on either of the numbers would reduce the number of things you have to check. It only makes sense to do it related to the smaller one to further reduce the number of things you're checking, but you're still reducing the number of things you're checking by a lot compared to the way we're doing it now. Okay, so really the square root thing is more of just kind of trivial knowledge. I'm just trying to get you to think about something algorithmically. And the bigger issue for that is, what we've been talking about, well, what we talked about last class was the time complexity issue. That you're not going to run into real often, but when you do run into it, it's a headache. All right, and you're not always going to know, oh, I'm going to go ahead and dive in and go and find the Euclidean algorithm to solve this problem, right? You might do that level of research if you're really writing a program that's super important that really needs to be fast. Then you go to that level of detail to make sure you have a very optimized algorithm. But in a pinch, you might decide, you know what, I can optimize this a little bit using a little math trick. That make sense? That's kind of what you're looking for with that square root solution, is a math trick. Okay, so in any case, if we were going to write this Euclidean algorithm real quick, static int Euclidean, actually, we probably just call it greatest common divisor. Int A, int B, while B is not equal to 0. T gets B, B gets A, mod B, and then A gets T. Okay? Then in the end, we're ultimately returning A. We keep whittling down A until it's our final answer. Okay? And we know we're done as soon as B hits 0. So as soon as we've continued to mod the heck out of B, we get down to the point where we have a final answer. So we'll return A. Okay? So now, for reduce, we don't have to do any of this. We don't even have to determine which is the smaller and which is the larger. All we have to do is say int GCD is equal to hw.gcd f0, f1, pass it our numerator and denominator in either order, doesn't matter. Okay, this guy will ultimately produce the greatest common divisor of these two integers. It has nothing to do with fractions. Okay, then we take that and divide both of our numerator and denominator by the greatest common divisor. That makes sense? Now let's see what our main looks like right now. Oh, we were doing some of that crap. So here's where we were making our fractions. And so I think we got it to the point where 3 fractions went pretty quickly last time, but 1,000 fractions didn't, right? There's 1,000 fractions. Realistically, we probably ran out of the precision of ints, so it probably zeroed back around. But point is, you see how quickly it happened. If we just make these fractions, well, here, let's do 100, see if we get a real answer. Might still zero around. Yeah, there we go. Punchline is, you see how fast it happened? Okay. Where if we had done that with our own, or our old reduce, it would have taken a lot longer. We'd still be waiting, and still waiting, and still waiting. Okay, so that's Euclidean algorithm. Not necessarily something you should commit to memory or something. It's one of those quirky little things that you might need. And most languages have them built into it. I'm not sure. Let me just check real quick. Math.gcd, no, not that. Is it integer dot? No, I know big integer has a GCD. I don't know where else it might be built into the language. I'm positive the big integer class in Java does have a GCD function that works on two big integers. Big integers are how we handle arbitrary size values. If it won't fit in an int or a long, we can use big integers, which are an object class, which we're going to start talking about today, to represent arbitrary size integers. The good news is that your homework assignment is going to be basically to write that big integer class, but not this class. It'll be next class. Oh, it's just an impossible assignment.
Maybe on Thursday, do when?
At the final.
When's our
I don't know.
Tuesday at 10.
Tuesday at 10. Oh, disaster.
final? Okay, fine.
Yeah, we'll talk about the final. So we might not have time for that homework assignment, but I'll give you one that's even harder.
Yeah.
Okay, so we want to start talking about objects. Now, up to this point, we've represented our fractions as things like something like that, right? So a 2-bucket integer array where bucket 0 is our numerator, bucket 1 is our denominator. Now, there's nothing necessarily wrong with this, but we can certainly understand that as we need to deal with data that becomes more and more complex, this little kind of duct tape solution is only going to go so far for us, right? You know, we're just kind of remembering that the first thing is the numerator, the second thing is the denominator. Not that big a deal for fractions. But what if we needed to control 10 pieces of information? Now we got to remember bucket 0 is one of the pieces, bucket 1 is another piece, bucket 2, well, what is that? Is bucket 2 social security number? Was it phone number? See what I'm saying? You start getting problems with that. So that's where this whole concept of object-oriented programming comes in. So this whole very first week of this class, very first day of this class, we talked about there being, 3 different kinds of programming languages. Object-oriented, procedural, and functional, right? We had our example. The procedural version of the telephone was just a pile of wires sitting over here. Object-oriented version of the telephone was something that actually looks like a phone. So we're going to start looking towards encapsulating our data within our own objects. We've been using objects like strings and random and things like that, but now we're going to start writing our own objects that we can then create variables from. All right, so what I'm going to do here is, we'll just do it inside this project. So I'm going to create a new class. So this is the first time we're actually having a program with multiple classes in it. Okay? Remember, all programs begin and end with main. So we're still going to have that main class that has our main method in it that will dictate what this program does. In our case now, though, we're going to create other classes that now allow us to create instances of our own objects inside of main or inside of our other classes. So I'm going to go ahead and create a new class. We're going to call this guy fraction. Okay? So we're going to create a new representation of fractions. So instead of using the stupid 2-bucket integer array that we have to remember, now we're going to have an int numerator, int denominator, and then we're going to have something called a constructor. Let me just say int num, int denom for right now. I'm going to show you a better way of doing that here shortly. Okay, so here's our simple kind of ghetto version of an object. This will allow us to create a quick fraction. There's nothing wrong with this, but I would call this poor programming practice, what we've written so far. And you'll understand why here in a second. Okay? But just to give you an idea on how, so right now this is pretty simple, right? These guys up here are called fields. So fields are variables associated with an object. Variables associated with an object. This guy is called a constructor. Then down here we might have a bunch of methods, which we haven't written any yet, but we've seen methods before, right? Okay. So all classes, all objects are collections of fields, constructors, and methods. Fields are variables that are owned by the object. Constructors are method-like entities which initialize an object, build an object for us. Notice that these guys look a lot like fractions with the exception that they do not have a return, or a lot like methods, except they do not have a return type. No return type there. Okay, and I'll explain why here in a few minutes. And then they can have 0 or more methods that might do something. In this case, we don't actually need any methods yet. All right, so that's our fraction class. Now, instead of saying int array f is equal to 1/2, I can say fraction f2 is equal to a new fraction 1/2. Both of these guys store the same data. They just do it differently. We're storing our numerator and denominator in a 2-bucket integer array here, which is very detail-oriented. So this is kind of like our pile of wires. We're seeing all the bone structure. Okay? Where this guy is an example of encapsulation. So we have this brand new variable type that we just invented, called a fraction. That's not built into Java. We just invented this. Name of our variable is f2. What does the new keyword do for us? Yeah, it's our real estate agent. Gets us a memory address. Okay, so the fact that the constructor, which is this guy, always returns a memory address. Okay, the fact that the constructor always returns a memory address is why constructors do not have a return type in Java. Because they always return the same kind of animal. They always return a memory address. Make sense? And I'm going to talk about that even more here in a few minutes. But that's the punchline where constructors think about them as being very much like methods, except no return type. And secondarily, the name of the constructor is always identical to the name of the class. That's in Java and also in C#. In Objective-C, that's not true. In fact, Objective-C is the language I'm going to show you in a few minutes that I like Objective-C as a teaching language to show you, it shows you all the details. Languages like Java optimize things for you, like why make the programmer put in a return type if the return type's always the same, right? That seems to be something that's good. That's a decision that Java made that's a good thing. Why make us waste time typing if we're always going to type the exact same thing? Make sense? Okay. But what it doesn't do is it doesn't show us the details that are being omitted. So we don't see some of we don't see the parts of the engine. And you might not care about the parts of the engine, but you should still at least know they're there at some point. Okay, so now that we've built our fraction, and let me just get rid of some of this crap down here. I can say system.out.println f2.numerator and f2.denominator. Make sense? So numerator, if you remember, at the time of definition, this kind of goes back to our class versus instance, blah, 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 are fields. And what are fields again? This is as good of an example as you're going to get, Trey. What are fields? Fields are variables built into an object. Okay, that's what fields are. It's a synonym for variables. We just happen to call them fields if they belong to an object. Okay. Now, if we're looking at a field used in the wild, is this a class field or an instance field? I'm asking you to lean on the knowledge you already have. It's not a curveball. Okay, tell me why you're wrong. Why did you think it was a class field?
Because it's not, or I think it's defined globally, so I figured that. And then,
What if I was talking about methods here? Is this a class method or an instance method? I'll even give you a little hint for something I'm going to be coming up with here in a few minutes. Let's assume this was a method. Is this a class method or an instance method? See, I don't think he believes you. Think it's an instance method? How do you know?
Because it's using F2.
Okay. It's being called by an instance of a class, right? Instance methods are called by an instance of the class in which it was defined. How are class methods called? By the name of the class in which it was defined. How are instance fields called? By an instance of the class in which the field was defined. How are class fields called, do you think? By the name of the class in which the field was defined. Exact same thing. So the follow-up question is, and I already gave you a hint on this, how do we know that's a field, not a method? Say this again? Yeah, parentheses. Methods take parameters, or at least have a parameter list. Not all methods have to take a parameter, but they at least have the opening and closing parentheses on them. Okay? So if I were to ask you on a final exam or a quiz or something like that to tell me, tell me what kind of animal is this? You would say the appropriate response should be, this is an instance field. It's a field because there's no opening and closing parentheses indicating that it's a method. And it's a instance because it's being called by the instance of a class. That make sense? Okay, so no real new knowledge there. We've just thrown the idea of variables, which you already knew, into objects. And everything else lines up. Class versus instance lines up just like class versus instance lined up for methods. Okay, so here's our fraction. That's how you could create one. And here's how we can access the numerator and denominator of the fraction. Maybe we now write a method. I wonder what I was typing there. Off a couple of keys. Maybe we write a display method for fractions. Rather than printing out the numerator and denominator here, I just say f2.display for it to display itself.
So you need to fraction dot display.
No. You can tell me why in a second. This thing's complaining about something. Oh, it's not complaining anymore. I just hadn't saved it. Okay. So that displays the fraction now. What kind of animal is this? Should be so quick for you guys at this point. It is a method. Okay, we'll start with that. How do you know it's a method?
Parentheses.
Parentheses. All right, good with that. What kind of method? Class method or instance method? Instance method. How do you know?
Because it's calling from F2, which is
Yeah, it's being called by an instance. Okay, so how are instance methods defined? At the point of definition, where we wrote this method, how do we tell the difference between an instance method and a class method? Static keyword. So static is there for which kind? Class methods. So that means static would not be there for instance methods. We look at fraction, notice no static next to display. Make sense? So we just wrote our first instance method. Nothing strange. We just didn't put static on there, which changed the rules of how we call that method. But there's some logic behind that. Okay, and we're going to talk about that here in a second. But first, I'm going to break our code. So any questions up to this point?
So why would you use this instead of the other method that we wrote using static? Because we made it look like a fraction somewhere else in the code.
Right, but now we've encapsulated all those details inside of our fraction object instead of all this crap down here, which we just see scary inside of our code.
Yeah, isn't it essentially the same thing? It's just it's located in a different
Pile of wires versus the thing that looks like the telephone. Both of them could be telephones. The procedural, this would be procedural code. So I could put a big pile of wires here on that desk and tell you that is a telephone. And you could search around for the different pieces and actually maybe make a phone call. But we prefer something that looks like a telephone, even though we know inside of that is all the wires and crap, right? So you're right. These are the wires. These are the guts. And what we would do is we would maybe make some changes, but take all these guts of that telephone, all these guts of that fraction, and pull them out of here and put them into the fraction object. And by doing that, we would no longer have to deal with all the details out here in main. So in fact, I'll just go ahead and do that. Just dump all this crap. Okay, so now look how much simpler main is. Now we could have a second fraction. Fraction f3 is equal to a new fraction 1/4, let's say. And then assuming we write the method, we can say fraction f4 is equal to f2 dot add f3. And then we could say f4 dot display. So now we have the same abilities. Now we haven't written the add method yet, but you could imagine that we could have an add method. And we'll write one here in a minute. Okay? We have the same abilities we had before, but look how clean our main driver is. This is the example of that telephone. We built 3 different telephones here. Here's one phone, here's another phone, and here's a third phone that was built in terms of the first 2. And we know that there's going to be all sorts of details underneath the hood of that phone. But doesn't this look a lot cleaner? This is object-oriented programming. Object-oriented programming is to encapsulate the details within the objects, rather than just having them all hang out here. Make sense? All right, so any other questions before I go and break this?
What's that error?
We didn't write the add method. I've pretended like there's a method there that isn't yet. We'll write it. So here I'll comment that out for now. Oh, and then I need to comment that out because now we don't even have a variable name f4. Okay, so now I'm going to break it. This is bad programming practice in my opinion. If somebody's going to look at the documentation for our fraction and they see that the constructor takes in 2 integers, those variable names should be as descriptive as possible. Okay, they should be as descriptive as possible. That means I want to call this guy numerator. And I'm going to call this guy denominator. So this would be my preference. When somebody's looking at the documentation, they should know what kinds of things I need them to pass in. Yes, it needs to be 2 integers, but because of the variable names, they should know that, oh, they need to pass in the numerator first, pass in the denominator second, in order for this thing to work. Okay? Similarly, within the fraction class, I'd like to name my fields numerator and denominator because that's what they are. This field's for holding the numerator, this field's for holding the denominator. Make sense? So these are desires that I have to have good variable names. But now we have a problem. When I say numerator equal to numerator, which numerator are we talking about right here? Which numerator are we actually talking about right here? The local one. We want to be talking about the field. Okay? We love to be talking about this guy here. But we're not. Why? Because a variable always resolves to its most local definition. The most local definition of numerator is this dude right here. That makes sense? Okay? But we need to have a way of accessing that guy up there. And we do that through a special keyword. Okay? Now, in the next 15-20 minutes, you need to pay very close attention. Because the entire structure of object-oriented languages is based on what I'm about to talk about in the next 20 minutes. And once you understand this, it makes the language much easier to work with. But it's a difficult concept to understand, even though it's an easy concept. Okay? We're going to be talking about the this keyword. Okay? This is how an object refers to itself from within itself. And let me show you this to you by example. Out here in our homework.java, we were able to say f2.numerator, f3.denominator, stuff like that, right? So here we've defined f2, and we are outside of the fraction class here. We're inside the HW class. So when I say f2.numerator externally, that's the same thing as saying if I'm in the particular instance of f2. Okay, so if I'm in this particular copy of fraction, the one that's associated with f2, that's the same thing as saying this dot numerator. So this says, and this is one of the reasons it's hard to talk about, is because it's hard to describe the this keyword without saying the word this a zillion times. When I say this dot numerator, I'm specifically talking about the field associated with this particular instance of this fraction object. So this dot numerator here, if we happen to be inside the instance associated with f2, is the same thing as saying f2 dot numerator here. Okay?
So giving us an error right there.
Just because I'm not using the fraction for anything. Actually, it won't give us an error in the end. This is probably complaining about. Oh, it's still complaining about the second one here. It'll be fixed in a second. So, This dot numerator is how we have to refer to ourselves because we do not have a variable in here called f2. If we say f2 dot numerator, it's not going to know what we're talking about. f2 is not in scope inside the fraction class. Externally, we know we're either talking about f2 or f3. Inside the class is this is how we reference this particular instance. So it's how we reference ourselves from within ourselves. So I can say this dot numerator is equal to numerator, this dot denominator is equal to denominator. So that version of numerator resolves to its most local definition, which is going to be these local parameters. But this version of numerator, we've given it a full path, if you will. We've told it exactly where it can find it. Rather than it having to resolve it to its most local definition, we've told it just go to the field associated with this instance. That make sense? So this is how we refer to ourselves. Now, this is a problem that I have with, that is a problem that I have with Java. Just like before, where they left out the return type for a constructor, they've also left out how this came into being. Okay? And I'm going to show this to you through another language. I'm going to show you some Objective-C code. So we'll go ahead and open up Xcode real quick. Let's see, I'll just start a new project. It doesn't, here, we'll just do this in an iPhone app. Doesn't really matter. Object test. Okay. So I'm going to go ahead, I'm going to create a new file. So this is like creating a new class that we did in Eclipse. So I'm going to create a brand new file, and this guy is going to be a Objective-C file. So that's equivalent to a .java file. Okay, we're going to call this guy fraction. Okay, so we'll go ahead and create the fraction class for us. Okay, now inside the fraction class, we're going to have, actually, let me do this a little differently real quick. Just so I can separate the two. Okay, do I want to do it without a header? That's fine. It's not going to kill anything. So I actually just ended up doing it the same way I did it before. Unimportant. All right, so we're going to have this thing called @implementation, and I'll just kind of, go through this crap a little bit. So I'm going to say class fraction. Well, we'll have a constructor. And in here, we're going to have a constructor whose return type is ID. So this is an instance method. In Java, instance methods just don't have static in front. Class methods do have static in front. In Objective-C, a minus is an instance method. A plus is a class method. So I'm creating an instance method here. And I'm actually going to take this out because this isn't even right anyways. I'm just going to show you what the method looks like. We're writing the constructor. Another difference .
Int n supposed to be on the inside of the
No, the int d is supposed to be on the outside. There we go. So right off the bat, constructors in Objective-C do not have to have the same name as the class. Okay? So that's one difference. So constructors in Objective-C are actually identical to methods. They're not like special methods. They are methods. Okay? And they also have return types. So this return type here, ID, means it's going to return a pointer, a memory address. Okay? So for every constructor you ever write in Objective-C, you will always have a return type ID. And then this is the name of the constructor. And this guy takes two parameters, n and d. Now, notice in our Java example, I wanted to call these parameters numerator and denominator for naming convention purposes, right? In Objective-C, method names are much more expressive. So, init fraction with numerator, so I'm spelling it out in English. Numerator will go into that variable, and denominator will go into that variable. Make sense? Self is equivalent to this in Objective-C. So up here we'd have an enumerator. So these would be our fields here inside the class. Here's our constructor. Here's us setting the numerator equal to the numerator and the denominator equal to the denominator. But notice what happens beforehand. Beforehand, we're saying self equals super init. So self is equivalent to this in Java. Super is equivalent to super in Java. Super is how an instance of a class refers to its parent from within itself. Okay? And that's an important thing to understand for this reason. Draw some pictures. All object-oriented languages are built this way. And I think we've seen this before. At the very top level, we have the great-great-great-great-great-great-great-great-grandparent of any object you might ever run into in the language. And that is a generic object called object. It's called object in Java. It's called Nsobject in Objective-C. Same thing. It's the parent of all objects. So this guy has special crap built into it that's part of what makes this language work. Okay? So that's the object class. Now for us, we're building one class beneath that called fraction. Okay? One class beneath it called fraction. Fraction's parent is object. So when fraction refers to its parent, super is the instance of object associated with this particular fraction. Okay? Now remember, I said that object has crap built into it to make the language work. The entire object-oriented language pivots on the existence of a top-level object. Okay? So right here in Objective-C, when I say self is equal to whatever my parent's init method returns, that's my parent's constructor, which I've just told you has magical powers. Okay? The person who invented this language built into that top-level object magic powers that knows how to generate that initial memory address. Okay? So even though we don't see the code associated with this init method, we know it does the proper magic of generating a generic pointer to a place in memory to hold an object. And we're going to set self in this case, or this in Java, equal to whatever's returned by our parent. Object is the most generic object that exists. So when we're creating a fraction, what happens first is we create an empty husk of an object, a generic object. Then we add some crap to that to make it a specialty object called a fraction. Okay? So create the empty husk, make myself special, then return a pointer to myself. And that's what gets returned as an ID. So what I'm telling you is that in fraction here, this won't work, but this is happening automatically. This is equal to object. Actually, this is equal to new object. And then return this. Those things are happening. We are instantiating a new variable called this. That's a pointer. We're doing all the special things that make this generic object less generic. Then we're ultimately returning a pointer, which is this. And we know this by, if I just take out comment out these two lines real quick. We know it's a pointer, and we've seen this before, because what works? If I say system.out.println F2, what's it going to display? Memory address. It'll display a memory address. That's proof that we are returning a pointer to ourselves here. And we've seen it with the random object, right? But we didn't see it with strings. Okay? Because strings have a special method built into it that makes the println method print right for strings. All right, questions about this? For homework, oh, go ahead. Well, I'll start writing this.
The definition is this is how an object refers to itself from within itself. So referring, is that like pointing?
Well, yes, but it's equivalent to like if we consider ourselves to be objects, and you say, "I have a meeting today." You're saying that you're telling other people that you have a meeting today, but I is how you refer to yourself. I don't go around and saying, Mike has a meeting today.
You could.
You could, but that comes off as weird, right? For homework, I'm going to create a single instance method here. It's going to return a fraction. It's going to be called add. It's going to boil down, or it's going to take another fraction as a parameter. This method should add two fractions, creating a new fraction that is the reduced result. That make sense? So you have to write this method such that out here we should be able to say fraction f4 is equal to f2.add and then display f4. Understand? All right. So I will give you these two pieces of code. I'll probably just paste it all in there, one after another, so you'll have to rewrite them into objects just to make life simpler for me. But in any case,
Shouldn't that go under methods?
huh?
Shouldn't that go under methods?
Sure. I mean, yeah, you're right. But those are just
Yeah.
just comments I put in there, right? It doesn't matter which order you have. You can have all your methods at the top if you want. But that's fine. This makes sense what I'm asking you to do? Okay, and that's due on Thursday. If you don't do a good job on this one, final's going to just be impossible. Just so terrible.
So can we use? So what we'll do is we'll use our